In this lecture, we will continue our discussion on confidence intervals and using confidence intervals to estimate population information. So when we build a confidence interval, we build it out of sample data and we use that information to make an estimate about the population. So in the last lecture, we used a population standard deviation in our calculations, and that's what's going to change with this lecture. We're going to be using a sample standard deviation for these problems, and the approach is going to be a little bit different. So in the real world, when we use sample data to estimate a population parameter, like a population mean, it's very unlikely that we will have access to a population standard deviation. So population parameters like the mean and standard deviation, if available, there would be no need to sample. So oftentimes we don't have access to the population standard deviation. And in those cases, we use the sample standard deviation instead. And we symbolize our sample standard deviation with a lowercase s, and the population standard deviation is denoted with the lowercase sigma. So this originated fairly recently in math history. It was in early 1900s. It was at the Guinness Company, the beer company. Chemist W.S. Gossett was working for Guinness and discovered this new test statistic called the t-score test statistic, which is different than z-scores. And in doing so, he was trying to make accurate conclusions about the population of beer using only very small samples. So the idea was not to use the entire population of beer, but to use small samples and make good conclusions, make good estimates about the population. So the t-score test statistic was not normally distributed like z-scores are. The distribution became known as the t-distribution. The t-distribution is going to be used when constructing confidence intervals for the mean of a population when you don't have the population standard deviation. That is, you don't have sigma. And you have a sample standard deviation instead. So the t-distribution is very similar to the normal distribution in the way it appears, but numerically it is different. They are both bell-shaped distributions. They never touch the horizontal axis in either direction. The area under the t-curve is also 100% as with the normal distribution curve. But small samples make the t-distribution more dispersed, which is more spread out than the normal distribution. It is lower and flatter. And as the sample size increases, the value of the sample standard deviation, S, gets closer to sigma, and the t-distribution looks more and more like a normal distribution. So as the sample size changes, the appearance of the t-distribution also changes. And here you see a couple of examples of distributions. The normal curve, that is the normal distribution, is here in brown. And there's a t-curve for a sample size of 12 and then another t-curve for a sample size of 5. And when the sample size is smaller, the curve appears lower to the horizontal axis, so it's flatter. So in our work, we are just generally going to refer to the t-distribution as a standard bell curve, but numerically it is going to have different values. So when we build a 90% confidence interval, we're going to notice that the middle 90% of the curve is cut off. And this t 95% here represents a t-score on the upper right of that cutoff portion. Now, why do you think it says 95% as its subscript? Well, let's look a little further. This one in the center is a 95% confidence interval, and it says t subscript 97.5. That's the t-score that cuts off the upper end of this portion. And with 99% in the center, the t-score that cuts off the upper end of the cutoff portion is T99.5. And you may realize now that number 99.5, 97.5, and 95 represents the area in its entirety to the left of the t-score. So there is 90% in the center plus an additional 5% in the left tail. That would make 95%. Then for this one, the 95% confidence interval, we have 95% in the center and an additional 2.5% in the left tail, summing up to 97.5. And for this one, 99 in the center, 0.5% in the left tail, and that's summing to 99.5%. So these three t-scores are the three t-scores we will be working with for the three confidence intervals we will be creating in this lecture. We will be building 90, 95, and 99% confidence intervals, and these three t-scores are the three that we care about. Now their values, and I haven't showed you yet how to get those values, but the values will be different based on different sample sizes because the t-distribution changes numerically based on the sample size. So when it comes to referring to the formula, when we build a 90% confidence interval, we're going to use a t-score labeled T95%, and that is because 95% of area lies to the left of the t-score that we need to use in our formula. Similarly, for a 95% confidence interval, we are going to use a t-score labeled T97.5%. And for a 99% confidence interval, we're going to use a t-score labeled T99.5%. So these are the formulas. Next page. Here they are. A 90% confidence interval is very similar in general form to the confidence interval for a population, using the population standard deviation. The difference is you use the sample standard deviation in the numerator here, and instead of z-scores, we're going to be using t-scores. So for a 90% confidence interval, use T95% here and here. For a 95% confidence interval, use T97.5 here and here. And for a 99% confidence interval, use T99.5 here and here. Other than that, the formula is very similar to the formula we used in the previous lecture. So how do we arrive at the actual t-scores? Because in the previous lecture, I told you that you would just remember that a 95% confidence interval uses a 1.96 and a 2.58 for a 99 and a 1.65 for a 90. But for the t-distribution, the change in sample size will change the t-score. So we're going to use the calculator to find out what the t-score will be for various confidence levels. So the function on the calculator is called inverse t. It's abbreviated with INVT, and it's in the same place that we've gone to find normal CDF and IMV norm. So it's second DISTR, and number 4 is INVT. And you'll find 3 inputs, area, DF, and then, just 2 inputs, area, DF, and then you'll scroll down and press paste. Okay, the area that you're going to enter represents the area to the left of the t-score. Now backing up a bit, the area to the left of the t-score is 95% for a 90% confidence interval, 97.5% for a 95% confidence interval, and 99.5% for a 99% confidence interval. So if we are to build a 90% confidence interval in area, we would put 0.95. The DF that you see here represents degrees of freedom, and that is found by taking your sample size and subtracting 1, and you'll put that here. It doesn't change your sample size. It's a different number altogether. So degrees of freedom is n minus 1. However, in your formula, you are still using the original sample size for n. Degrees of freedom is simply used to find out what the t-score will be. So if we suppose we're doing a problem where the sample size is 10 and we want to find the value for a 90% confidence interval, so that is we want to find the t-score T95, we will enter a 0.95 for area and a DF of 9, which is 1 less than 10. Okay, 0.95 for the area to construct a 90% confidence interval and a DF of 9, which is 1 less than the sample size. And if you scroll down to paste and hit enter, your t-score is this long number here, and we are going by convention, we are going to round it the same way we've done with z-scores, round it to 2 decimal places, and that would be 1.83. Okay, 1.83.